Welcome back to The Explainer. Today we're taking on a genuinely massive engineering challenge, decoding the ultimate flow meter comparison matrix. Look, if you've ever stared at industrial flow measurement data, you know exactly how overwhelming it can get. We're talking about a source matrix with 6 different meters and a staggering 72 unique data points. But hey, don't worry, I'm super excited to break all of this down for you. And rather than just throwing some giant, dense, unreadable image on your screen, we're actually going to draw this data out piece by piece. We're going to map out a really simple, logical guide. By the end of this, you are going to know exactly which meter to use and, more importantly, why.
Okay, let's dive right into this roadmap. First, we'll tackle the industrial flow challenge. Then, we're going to group these meters into categories: our everyday volumetric workhorses, the precision pipeline specialists, and the high-tech heavyweights. After that, we'll do a head-to-head performance and maintenance showdown. And finally, we'll wrap up with a cheat sheet for making your final selection.
All right, Section 1, the Industrial Flow Measurement Challenge. Before we do anything else, we really need to ask, what exactly are we measuring here?
So the absolute crucial point here is understanding the core difference between volumetric flow and mass flow. Think of it like this. Volumetric flow tells you the amount of physical space a fluid takes up as it moves, like gallons per minute. Mass flow, on the other hand, tells you the actual physical mass or the weight of that fluid moving through the pipe. When we look at our data, it's pretty wild. 5 out of our 6 meters, that's the differential pressure, turbine, electromagnetic, ultrasonic, and variable area meters, all measure volumetric flow. Just 1 meter on our entire roster, the Coriolis meter, directly measures mass flow. This fundamental difference literally dictates everything about how these devices are engineered and, how they're priced.
Moving on to Section 2, the everyday volumetric workhorses. Let's look at the simple, low-cost veterans of the industry. Now, both of these meters are super budget-friendly, ranking low on the cost scale, but they operate on very different, albeit simple, mechanical principles. Picture drawing a straight pipe and then inserting a literal restriction, like an orifice plate, smack in the middle. The differential pressure, or DP meter, measures the pressure drop right across that physical hurdle. Because of that, it absolutely requires straight, stable pipe runs both upstream and downstream, just to make sure the flow is stable before it hits the restriction. Now, instead of that, visualize drawing a tapered vertical tube with a little physical float inside it. That is your variable area meter. As the flow pushes up, the float rises. This means its installation rule is incredibly strict. It simply must be mounted vertically.
But, low cost always comes with trade-offs, right? Because you're literally forcing fluid through a physical restriction in a DP meter, you cause a permanent high pressure drop in your system. It also has a pretty low turndown ratio, just 3:1 to 4:1. Basically, it can't measure a very wide range of flow rates. Then you have the variable area meter. Since it relies on that rising float, it's completely unsuitable for thick, high-viscosity fluids. It handles solids really poorly, and it gives you the broadest accuracy margin on our entire list, sitting at plus or minus 2 to 5%. Look, they're cheap, they're reliable, but they are definitely not the most precise tools in the shed.
Okay, let's shift gears to Section 3, the precision pipeline specialists. This is where we get into the turbine and electromagnetic meters.
To really understand the electromagnetic, or mag meter, you have to visualize Faraday's law of electromagnetic induction. Picture an open pipe, but instead of a physical barrier inside, imagine drawing this invisible magnetic field completely across the inside of it. As conductive fluid passes through that magnetic field, it generates a voltage that's directly proportional to the flow velocity. Honestly, it is an incredibly clever, totally non-intrusive way to measure flow.
And this brilliantly illustrates a key head-to-head clash in our data when it comes to fluid compatibility. The turbine meter literally relies on a physical, bladed turbine spinning right in the middle of the fluid stream. Because of that, it is strictly for clean liquids and gases. Its solids handling is rated as poor. Throw a heavy slurry at a turbine meter, and you're just going to break it. But the mag meter, because it uses those invisible magnetic fields and has a totally open pipe, it actually excels with slurries and boasts good solids handling.
There is a catch, though. The mag meter has one massive, absolutely non-negotiable caveat: greater than 5 microsiemens per centimeter. That is the strict minimum conductivity threshold required for an electromagnetic meter to even work. If your liquid isn't conductive, like say pure hydrocarbon oils or highly purified water, Faraday's law isn't going to help you. The meter simply won't read the flow. Zero. Nothing.
All right, moving into Section 4, the high-tech heavyweights. Let's talk about the ultrasonic and Coriolis meters, our advanced problem solvers.
So, the ultrasonic meter works using something called the transit time difference of ultrasonic waves. It literally shoots sound waves diagonally across the pipe, both with the flow of the liquid and against it. By measuring exactly how much the flow speeds up or slows down those sound waves, it calculates the velocity. What this means in practice is that it requires minimum straight pipe, it can handle clean or dirty liquids and gases, and maybe best of all, it results in a very low pressure drop, simply because there's absolutely nothing blocking the flow. And then we have the true heavyweight champion of the matrix, the Coriolis meter. Picture drawing a U-shaped tube and vibrating it. As fluid flows through this vibrating bend, the actual mass of the fluid forces the tube to twist just slightly in response. That right there is the Coriolis force. Tiny sensors measure this microscopic twist to calculate exactly how much mass is moving through. And because it's based on this direct physical relationship, it can measure direct mass flow, density, and temperature, all at the exact same time. It's pretty wild.
Now, what's really interesting here is comparing these two heavyweights side by side. Both of them give you a very low pressure drop. But look at the capabilities. The ultrasonic is a volumetric meter with an accuracy of plus or minus 1 to 2%, and it comes in at a medium cost. The Coriolis meter, it provides direct mass, density, and temperature, with a frankly jaw-dropping accuracy of plus or minus 0.1 to 0.2%. It is hands down the most precise instrument we have here, but you definitely pay for it. It's literally the only meter on our entire list categorized as high cost.
Let's step back and look at the big picture in Section 5, the Performance and Maintenance Showdown. Let's see how all 6 stack up.
When you look at the accuracy data across the board, 3 distinct tiers immediately emerge. Down at the bottom, providing a pretty broad estimate, is the variable area meter at plus or minus 2 to 5%. Then, in this massive middle ground, we've got meters ranging from the DP at 1 to 3% all the way down to the highly accurate electromagnetic at 0.2 to 0.5%. But sitting entirely in a league of its own, all by itself, is the Coriolis meter at 0.1 to 0.2%. Listen, when every single drop of fluid translates directly into dollars, this data just proves that you truly get the precision you pay for.
Another massive performance metric we have to talk about is the turndown ratio. That's essentially the range of flow rates a meter can accurately measure. 100 to 1. 100 to 1. That is the incredible turndown capability shared by the electromagnetic, ultrasonic, and Coriolis meters. Compare that to the super limiting 4 to 1 ratio of the differential pressure meter we talked about earlier. Seriously, if your industrial process experiences huge, massive swings between low flow and high flow, these high-end meters aren't just nice to have, they're an absolute necessity.
So what about actually keeping these things running? Well, the maintenance data is pretty fascinating. 5 out of our 6 meters are rated for low maintenance. The one single exception, the turbine meter. It requires medium maintenance. And the reason is super simple. It relies on physical moving parts inside the fluid stream. Moving parts wear out. Simple as that. This also ties in perfectly to the solids handling data. Variable area and turbine meters both have moving components. And guess what? They both offer poor solids handling. Meanwhile, that Coriolis meter, with its open, vibrating tube design, boasts excellent solids and slurry handling.
Okay, let's bring it all together in Section 6, making your final selection. Let's see how this builds into an actual cheat sheet.
Matching these meters to real-world applications is the final piece of this giant puzzle. Look, if you just need general-purpose measurement, maybe you're working with steam or you've got low-flow air applications, your cost-effective DP and variable area workhorses are going to be your best bet. Now, if you're dealing with clean liquids, hydrocarbons, or general HVAC water, you're going to want your turbine and ultrasonic specialists. But if you are tackling brutal wastewater, super dense slurries, or you require the absolute pinnacle of accuracy for things like chemical batching or custody transfer, you've got to step up to the electromagnetic and Coriolis meters.
And that brings us to the ultimate question. By matching up fluid compatibility, required accuracy, and your budget, you are now completely equipped to navigate this matrix. You know that a Coriolis meter is brilliant, for sure, but you also know there's no way you should put it on a simple cooling water line where a much cheaper ultrasonic would do the trick. So which meter solves your specific flow challenge without paying for precision you just don't need? Take these facts, apply this logic to your own facilities, and make your next engineering decision with absolute confidence. Thanks for joining me on this explainer, and as always, keep learning.